What are you thinking about?
I'm trying to understand the computation of something in an approximate way. So it's a kind of math problem. But I mean, it's based on some physics model, and you have to compute the properties of this. This is a model that was proposed by some condensed matter physicists that has some properties that make you think that it's going to be related to a gravitational system. And so I'm trying to understand the computation of certain properties in this model.
Is it like that you are checking this model or redo what he has done, or do you want to use it?
Eventually I want to use it, but right now I'm trying to understand it and understand the computations. So one can do some computations numerically, and we observed a certain property numerically, and we are trying to understand analytically, or just with the formulas, exactly where it's coming from.
And do you succeed?
I haven't succeeded yet. I've been thinking about this for a few days.
You're thinking about this for a few days?
Yeah, to match these two computations.
So what is the problem?
This particular... it's a model of interacting fermions, so interacting particles. More precisely, I should say interacting quantum mechanical degrees of freedom. So interacting qubits, if you wish. And they interact with some random interactions, and at low temperatures they have properties that are similar to properties that black holes have. The thermodynamics of this model is similar to the thermodynamics of black holes, in particular of black holes that are near extremal. So when you have black holes that carry charge, there is a limit to their mass, so their mass cannot be too small. The mass can be arbitrarily big. So for a fixed charge, the mass can be very big, but there is a lower limit on the mass.
Yeah, you explained it yesterday.
Yeah, well, then when you reach to this lower limit on the mass, the temperature of the black hole becomes very small, and the black hole develops an approximate sort of scaling symmetry. Scaling symmetry means that physics looks the same at various energy scales, and the geometry also develops this approximate symmetry where you can be the physics at different distances from the horizon looks essentially the same. So if you are 1 meter from the horizon, it looks somewhere you go half a meter. Everything looks the same except that the energy gets rescaled. So in these extremal black holes, the symmetry is realized in a very special way, and this model seems to realize it also in that special way. So I'm trying to understand the connection between these two things. In particular, the symmetry determines how the specific heat of the black hole behaves, or how the entropy of the black hole behaves, and so I'm trying to understand this feature. Trying to understand it in the simplest way and from symmetries. But right now I'm not trying to do that. I'm just trying to compute what the answer is in a particular model without necessarily using the symmetries. There is some way of computing it using the symmetries and a direct way of computing it and trying to understand the relation between the two. Well, this is a bit technical.
Yeah, it's very technical. But
yeah, I guess in general I could say that one of the goals of physics, or the work we do, is trying to understand how the role of symmetries, how symmetries govern different behaviors. Because sometimes you look for universal answers, so you can have some models and the details of the models can vary, but sometimes you find that the answers in the end are all similar. And some features are similar, some features are different. And usually there is some symmetry that determines the common parts of the answers, so the things that are common to all models. And that's the thing that is interesting to understand in general, because doesn't depend on the details of the model, but just on some more generic features.
Any moment there's a colleague of you coming here.
Mm-hmm.
Can you tell me who's coming?
Yeah, the person that's coming is Daniel Jeffries, who's a professor at Harvard. So we worked on a paper recently, and we are discussing some other ideas. So the paper was about the connection between entanglement and geometry, and this is something a group of us has been thinking about, and we are just going to discuss this further.
Well, let's wait for him.
We are doing this reconstruction from all the local operators here. Right? Well, at least in principle, all the local operators everywhere are sufficient.
But in this case, because you have Juan symmetry, I think the mirrors are kind of local. It's like in the thermofield double. I don't know.
I'm not entirely sure if I got the point.
Well, you can go to
Well,
the
I mean,
other
like
room
for
now.
in the entanglement wedge reconstruction, I think we expect probably to use the modular Hamiltonian to express. Well, yeah, I don't know.
Which are the same as the operator. So in this situation, they are the same as the other operators, right?
Yes.
But when we want to do the Rindler reconstruction, right, we are interested in expressing everything in terms of operators defined here. Right?
Yes. I mean, in this case, it's a little weird because they are local, so it's what you will naively think that you will get, but.
No, but if we do the mirrors of these operators, we'll get
You get those operators.
we get operators which
Yes,
are here,
yes.
right?
Yes, I was thinking that maybe if we have the global representation, maybe we can express the operators which are not in this region as the mirrors of the operator. So, okay, well, I mean the operator. Okay, so the mirrors of these operators are operators which will act here, but they will look like they act outside.
No, there will be the operators that act outside, because for doing the mirror construction, you will have to use the global state, right?
Yes.
Not just the density. You cannot define them using the density matrix here.
Yes.
You have to define them using the full state, right? Yeah, this is similar to what we discussed the other day. I was also.
Yeah, it's kind of funny.
Yeah.
Right. Because you need the full state, although the formula for the mirrors looks like it. Yeah.
Yeah, it looks like they refer only to these operators, but because you have the full state, really defines the operators acting on the other side.
Yeah, I mean, I guess, yeah. I mean, I guess I wanted to see if there was some reason why we expect entanglement with reconstruction to happen or not, and maybe, well, yeah. Because, I mean, the formula that we proposed could look a little funny, the one where you express it in terms of modular float operators. So, yeah, I mean, I don't know if there is some way to check whether that should be true in principle.
Well, we could check whether it's true in
Sorry to
practice,
interrupt,
right?
but do you want to move to the other room? Is that okay?
It doesn't matter to me. Okay, sure. It's a small room, right? Yeah.
Well,
Right, I mean, like, for instance, you don't expect to Rindler reconstruct the operators outside the Rindler wedge.
Yes.
Seems like sense. So,
Yes, I mean, you know, with entanglement wedge, it's hard to see what you, yeah.
yeah, I mean, but
The spectrum is a fundamental output.
yes. Yes.
something like,
Well, given.
but I mean, in the paper that Arlo and Shi Dong and Aaron Wall wrote, they wrote some kind of formula, although it's a formula that's not very explicit exactly.
What you mean in their last
The
paper?
last paper, which I didn't entirely understand actually.
Okay, I think that for my understanding, the last paper we could sum it up in two lines from our perspective, which is just to say that if you act with a unit, so I think what they are saying is that if you have the entanglement wedge, so this is R B, and this is. So I think what they are saying is that if you act with a unitary here, a unitary of a local operator here, this doesn't change the density. This doesn't change the. Okay, so first the relative entropy of. So it doesn't change the relative entropy in the bulk of RB. So it doesn't change the relative. So the relative entropy in the bulk of R in the boundary of R doesn't change.
Yep.
So then they conclude that this operator commutes with all the operators here. I think that's all they say.
In some sense.
Yes. So what formula did you see? Did you say?
Well, maybe. Okay, I don't know. I'm not sure if I saw it in the paper, or if Dan Harlow said it to me now, actually. But it wasn't very explicit anyway. Like, he didn't write the formula on the board, but he said something like, if you knew the mapping between. Somehow he thought if you knew the full mapping, like the global mapping, then you could get a kind of formula.
The global mapping, you mean if you can reconstruct the operators here from
things everywhere, yeah,
okay,
something like that. Yeah. I think that was roughly the content, but
okay.
it was a brief discussion. So,
Well, yeah, I mean they have a formula in the appendix in the ADH appendix.
yeah, it might be this.
So yeah, where they use this is way of getting the effective members by using like Tomita Takesaki, something like that. And he was, I mean, the quantum error correction formula was very similar to that.
Okay, I see.
Well, let's see, for our purposes of trying to see whether the formula we propose in our paper works, I mean, we could just use the Cassini-Huerta discussion and really check it, right?
Right. You mean you
maybe-
use the modular flow to evolve the operators in the interior and see what.
Yeah, what
equation
kernel?
you get,
Yeah, what kernel you
basically.
get,
Yeah,
or maybe there is a formal way to do it. You don't have to do it when.
Yeah, I mean, I try to. I'm not very good. I mean, okay, I think the problem is that the formula is in the lattice, and they say that this kernel. So you have like 2 or 3 kernels, and at the end you end up getting one kernel, which is you have like the x's and the p's, and they say that like they are not well defined in the continuum, but then when you combine them, they are well defined or something.
Okay, yeah.
So it's a little tricky.
But in the end, isn't their kernel defined in terms of some Green's functions and the
Yeah, it's
inverses?
pretty explicit.
Yeah. But you have to do the inverse of a Green function, and take the log and all these things.
Yeah.
So they do it for the fermions, and they can do it because you can construct the resolvent.
Do we remember what the formula is?
For the fermion, in general.
The general
But
formula in terms of Green. So I've forgotten.
But I think it has something like log. I think it has something like log of c minus 1 minus c minus 1 to the minus 1, and I think maybe here you have something like x and then something like over c minus 1 or something. This is, okay, so this may be the one. I think this may be the one for. I think this is one. Okay, so for the scalar fields you have scalars and bosons, and I think this. I mean, the fields and the momentum, and I think this will be the one for the fields.
Okay.
So where C.
So this is the modular Hamiltonian field basis, basically.
Yes, but you have this for the. So you have a contribution from the fields and one from the momentum.
Right.
Oh,
There
right. I
is
see.
the-
Yeah.
And this is, I think, is the square root of xp, where
Right.
yeah. So x is the 2-point function of the,
Oh, the
of the
axis and-
fields.
yeah.
Thought about the large mass limit a little bit, hoping that maybe it would simplify, but. Well, in the large mass limit, x and p become closer to being local, but it's a difficult starting point.
How do you go from this one to the formula for the Rindler wedge?
That's a good question. Yeah, I even asked Cassini, and he said.
I see. I
No.
thought that was supposed to be easy.
No. I asked Cassini. Because that would be a good place to start, just to see to what extent these formulas for an arbitrary region reproduce the Rindler formulas close to the boundary of the region. But he said, well, of course it has to be the case, but.
But he didn't know how to do that. So, yeah, interesting.
The kernel should be local when, in some sense, when you apply it to operators which are close to the boundary of the region.
Right.
Yeah, it's hard to
Well, I guess if one
Helps you
could
just
show that
follow
it obeys a certain differential equation, or yeah, of course, it's.
Yeah.
But maybe there's a. Somehow.
Why does it have this form? I mean, I thought it should involve some matrices that you construct from correlators inside and also outside.
No, it's only based on stuff inside.
Yeah.
Because you basically, the only input that you want to put is that it has to
Yeah,
be
of course,
produced,
yeah, it has to reproduce the things
Yeah.
inside. Let me see.
Yeah. I mean, when you.
Yeah, I mean, I was thinking. Yeah, I think there could be some implicit equation, but yeah. I mean,
Yeah, I mean, if you compute something like I mean, if you compute just powers of the density matrix, then this is some calculation where you just insert some operators into the replicated geometry.
Well, that's computing
Right.
correlators, right? But this is a formula for the Hamiltonian stuff.
yeah, but you would like to compute maybe the commutator with the modular Hamiltonian, and then from that get
Something like that. Yeah. Yeah. Maybe you could compute the commutator with rho to the n, and then try to continue n. Maybe this is not going to be useful, but yeah, perhaps this continuation is going to be impossible in practice. Like you won't get an analytic formula or something.
Yeah, I mean, and about that, I think it classically is very clear. But but you want to get some quantum contribution, so you are not only changing the geometry, but also changing the state. So that's a little trickier to see how it plays a role.
So what are you talking about?
It is well, I mean, when you go to the replica geometry, then you will have a contribution from n, which comes from the real bulk modular Hamiltonian, and a contribution.
Of course, yeah. In gravity, you mean?
Yes,
I
yes,
suppose.
yes, in
But
gravity.
But here the problem was to do this in quantum field theory.
Yes,
right?
I agree.
Because that was because this was a bulk computation in the quantum field theory in the bulk, so
Yes.
we wanted to.
I guess that. Yeah, I mean, to compute the log, normally what people do is to have this integral representation when you want to compute the log for the relative entropy, for example. So maybe that's something I was thinking too. Like maybe one can go to modular Fourier space somehow, and then things are simpler there. Which I think.
Where it is Fourier space in some variable that you.
Yeah, and then smooth. The only thing that relates. I don't know.
I mean,
the replica trick is not too hard because you can do for the correlators you can do the image method, but I guess doing it for an arbitrary region in AdS is pretty tricky.
Well, the simplest, I think, situation would be the simplest thing would be to see whether this can be related to a slightly more explicit formula and.
I guess, yeah. This formula is not very useful, so you should be. One should try to rederive it in a different way, probably.
But well, the formula is correct, and it's just that you can have the hope that it's rewritten in a simpler way. But, ¿Para la derecha hay un frío?
No, pero...
Ah, por allá. Pero la mía le va a dar frío ahora. Vamos a ver para allá ahora. Para la derecha. No sé, derecha, derecha. Después la derecha. Y ahora nos van a venir con el auto. Chicos, vénganse más cerca.